Hello students, today we will see the second part of the video of chapter 11, thermal properties of matter. So today we will see thermal expansion. Thermal expansion, in a common experience that most substance expand on heating and contract on cooling. A change in temperature of body cause change in dimension. The increase in dimension of body due to increase in its temperature is called thermal expansion. We'll see now the types of thermal expansion. The first one is the linear expansion. The expansion in length is called linear expansion. If the substance is in the form of long rod, then for a small change in temperature, let del T is the change in temperature here. So the fractional change in length is del L upon L, and the del T is directly proportional to del L upon L. So we can write here when thermal expansion is there in the form of the linear expansion, that means you can say if we are taking a thin rod, that means its radius or the thickness of the rod is very small in comparison to the length of the rod. So in such situation, when we are giving temperature to the substance, this rod, so the increment in length would be there. Suppose the initial length of the rod is L and the final length is L dash. So change in length is L dash minus L, which we will write as del L. Okay. Fractional change in length, that is del L upon L. Change in temperature, that is final temperature minus initial temperature. This is del T is equal to T2 minus T1. T2 is the final temperature and T1 is the initial temperature. So as indicated or the state before, the fractional change in length is directly proportional to change in temperature. As we increase the temperature, the length fractional change in length also would be increased. So they are in direct proportion. So del L upon L is directly proportional to del T. That means del L upon L is equal to, here what we have done, the proportional sign we have removed. So a proportionality constant we are putting here. This is alpha. So del L upon L is equal to alpha del T. This alpha is a proportionality constant called coefficient of linear expansion. Now we'll put the value here. Del L is what? L dash minus L, and upon the original length L here is equal to alpha, and del T is T2 minus T1. When we simplify it, this L can be transferred here, will multiply. So L dash minus L is equal to alpha L T2 minus T1. Then we'll transfer this L here. This is minus L. So if it will transfer here, it will become positive. So L dash is equal to L plus alpha L T2 minus T1. So this is the equation here for the change in length, means for the extension in length, that is L dash is equal to L plus alpha L T2 minus T1. Actually we can take L common here, so we can make this equation like this. L dash is equal to L, we will take common here, so it will become 1 plus alpha T2 minus T1, or we can write this as L dash is equal to L 1 plus alpha del T. This, so according to the question or the case given, we will apply this formula also, this formula also, and this formula also. Any one formula we can apply according to the. Now we will see area expansion, or we can say this as a superficial expansion also. For this, first of all, we will consider here a square shape. This sheet is there. This is a plane surface. So you can say the length of this plane surface is L and the width is also L. So when the increment will take place, means when we are giving temperature to it, So after getting temperature, the expansion will be there. This is del L, and here also del L you can say. So anyhow you will find here, if length is increases, width is increases, so area also will increase. So here you will find the initial area is suppose A and the final area is A dash. So change in area is del A, which is A dash minus A. Fractional change in area is del A upon A. Here we will see the expansion in area is called areal expansion or the superficial expansion due to increase in temperature. If a plane substance expand for a small change in temperature del T, so the fractional change in area is directly proportional to change in temperature. Because fractional change is directly proportional to temperature, so here we have seen already the change in temperature. This is del T is equal to T2 minus T1, and the fractional change in area, which is directly proportional to change in temperature. Fractional change in area is del A upon A, and it is directly proportional to del T. If we just remove the proportional sign, we'll put again a constant which is called a coefficient of areal expansion. So this del A upon A is equal to beta del T, and this beta is the proportionality constant called coefficient of areal expansion. Now you will put the value of del A here. So you will find here A dash upon A dash minus A upon A is equal to beta T2 minus T1. So A, you can transfer this side, so it will become A dash minus A equal to A beta T2 minus T1. Now transfer this minus A this side, so you will find A dash is equal to A plus A beta T2 minus T1, or if you will take A common, so A dash equal to A1 plus beta T2 minus T1, or we can write this formula like A dash A is A1 plus beta del T also we can write. Okay, so here beta is the proportionality constant called the coefficient of areal expansion. A dash is the new means area, you can say. This is A is the original area, then T2 is the final temperature, T1 is the initial. Volume expansion. Here you will see we have taken a cube, and as the temperature is initially it is T1, when we are giving temperature up to T2, then the expansion would be there in the length, width and the height. So means overall the volume will expand. So in this expansion, the expansion in volume is called the volume expansion, and the fractional change in volume is directly proportional to change in temperature. So suppose here initial volume is V of this cube and the final volume is V dash. So fractional change in volume is del V upon V. Change in temperature is del T, and it is equal to T2 minus T1. As stated earlier, fractional change in volume is directly proportional to change in temperature. So del V upon V is directly proportional to del T. That means del V upon V is equal to, we'll just remove the proportional sign. So we'll find here gamma del T. Okay, so this gamma is a proportionality constant, and it is called the coefficient of volume expansion. So now the formula become del V upon V is equal to gamma del T. We'll put the value here of the del V, that is V dash minus V upon V, and is equal to gamma del T. In place of del T we will write T2 minus T1. Now we'll simplify this formula. So we'll get here V dash is equal to V in bracket 1 plus gamma T2 minus T1. So this is for the volume. Relation between alpha and beta. Alpha is the coefficient of linear expansion and beta is the coefficient of areal expansion. So we will find out the relation between the coefficient of linear expansion and coefficient of areal expansion. For this we have taken here a sheet of length L and width L, that means it is a square shape sheet. And when we give the temperature to this sheet, then the del L, the means the width also will increase and the length also will increase in the same amount, that is del L. Suppose, so in such situation the initial length is L, the final length will become L dash, which is equal to L plus del L. Then the initial area is A, which is equal to side into side, that is L square. Final area is A dash, which is again side into side, but this time side will become L plus del L, so it will become L plus del L the whole square. Now change in area is del A, which is equal to final area minus initial area. Final area is L plus del L the whole square, and the initial area is L square here. Here we will just apply the identity A plus B the whole square. So the same way we will get here L square del L, L square 2L del L and del L square. Okay. So we'll find this L square would be cancelled, remaining 2L del L plus del L square. Now we'll see that this del L is a very small quantity, so squaring of a small quantity will become more smaller. In that case we can neglect this quantity del L square, so we'll get only 2L del L. That means del A is equal to 2L del L. Now just divide here the area, that is A, in the left hand side as well as in the right hand side. So del A upon A will become 2L del L upon A. Now del A upon A is equal to 2L del L. In place of A we can write L square here. So 1L would be cancelled and it will become 2 del L upon L. So here in the left hand side you will get the fractional change in area. In the right hand side you are getting the fractional change in length. So double of the fractional change in length. Fractional change in area is equal to alpha del T. You know that fractional change in area is equal to alpha del T, and fractional change in length is equal to beta del T. This is opposite only. The fractional change in length is equal to alpha del T, this one, and the fractional change in area is equal to beta del T. Okay, we'll just put the value here. So what we will get, in place of del A we will get beta del T, and in place of this del L upon L we will get alpha del T. So this is 2 times alpha del T. Del T would be cancelled here, so it will become beta equal to 2 alpha. That means the relation between alpha and beta is like that. The coefficient of areal expansion is double of the coefficient of linear expansion. We'll see relation between alpha and gamma. Alpha is the coefficient of linear expansion and gamma is the coefficient of volume expansion. To prove the relation between these two, we have taken here a cube of length L, side L, and as we are giving temperature to it up to T2, then the expansion in every direction, every dimension would be there. That means in length, in width and in height. So everywhere, suppose the increment in length, width and height is like del L. So initial length is L here. The final length will become L dash, which is equal to L plus del L. Initial volume is V, which is equal to L cube, and the final volume is V dash, which is equal to L plus del L the whole cube. Now we know that change in volume, that is equal to del L, change in volume, that is equal to del V, and this is equal to V dash minus V. V dash is L plus del L cube and minus this V is L cube. We'll just apply the identity here, that A plus B the whole cube. So the del V will become that this is L cube plus 3L square del L plus 3L del L square plus del L cube minus L cube. L cube would be cancelled here, and as we know that del L is a very small quantity, so squaring and the cube of this quantity will also smaller, means very small, and we can omit that quantity. That means we can neglect these quantities L square and del L cube. So we'll just leave the terms which include this del L square and the del L cube. So the remaining term is now, this is del V is equal to 3L square del L. So we'll divide both sides with the volume, the original volume. So del V upon V is equal to 3L square del L upon V here. Now del V upon V is equal to 3L square del L. In place of V we can write L cube. So you can see here the L square from the numerator and L square from the denominator will be cancelled. In denominator 1 L will remain, and in the numerator 3 del L will be there. So del V upon V is equal to 3 del L upon L. Del V upon V, we know very well this del V upon V, the fractional change in volume, is directly proportional to change in temperature, and we have taken out this is equal to what? Gamma del T. Here the del L upon L, this is the fractional change in length, will give us alpha del T. So when we'll just put the value here, this is gamma del T is equal to alpha del T. So what you will find, del T would be cancelled. Then remaining one is what? Alpha, sorry, gamma. The gamma, this is 3 alpha. Here it is 3, so it will be 3 alpha. So gamma is equal to 3 alpha. That means the coefficient of volume expansion is 3 times of the coefficient of linear expansion. This is our equation 2. In equation 1 we got there, that is the beta is equal to 2 alpha. In equation 1 we have written this is beta is equal to 2 alpha. Now we'll just from equation 1 and 2, what we can write here? In equation 1, if we'll multiply with 3, and equation 2, if we'll multiply with 2 both the side, we'll get here this is 3 beta is equal to 6 alpha and 2 gamma is equal to 6 alpha. That means the 6 alpha is equal to 3 beta and 6 alpha is also equal to 2 gamma. So we can write this relation in combined way. This is what? The 6 alpha is equal to 3 beta and that is also equal to 2 gamma. So here is the relation between all three, that is the coefficient of linear expansion, coefficient of areal expansion and coefficient of volume expansion. So what relation we got here? That is the 6 times of coefficient of linear expansion is equal to 3 times of coefficient of areal expansion is equal to 2 times of coefficient of volume expansion.